In the previous video, we zoomed in on what happens when a solute is dissolved in a solvent. Today, we'll conclude Unit 4 by talking about solution stoichiometry. This should be quite a short video, since most of the concepts have already been discussed in our unit on regular stoichiometry. Solution stoichiometry is crucial to a lot of laboratory techniques though, so that is why we're reviewing it as we end this unit. Let's begin with a brief review. We now know that only a certain amount of solute will dissolve in a given amount of solvent. The parameter used to measure this is called solubility. There are three adjectives used to describe solutions. An unsaturated solution is one in which the concentration of solute is less than the solubility. This means that we can continue adding solute to an unsaturated solution without the fear of the solute being unable to dissolve. Once the dissolved solute concentration becomes equal to the solubility, the solution becomes a saturated solution. If we continue adding solute past this point, the solute thus added would fail to dissolve. It would instead gather at the bottom of whatever container the solution is contained in, and the solution itself is said to be supersaturated. We should also recall that like dissolves like. Nonpolar solutes dissolve in nonpolar solvents, and polar solutes dissolve in polar solvents. Another thing to keep in mind going forward is that for solid solutes being dissolved in a liquid solution, an increase in temperature increases the solubility. For example, hot water can dissolve more sugar than cold water, and this is something a person can test rather easily. Our focus for today is on chemical reactions which occur inside solutions. Whenever we want to determine how much of a solute must react with a solvent to produce a product, we must use solution stoichiometry. In such instances, the solute and solvent are both reactants. The most simple cases are those in which an ionic compound is dissolved in a solution. As we already know, ionic compounds split into their constituent cations and anions when they are solvated. From here, these cations and anions become reactants that can react with the solvent that is dissolving them. As a quick reminder, solutions that involve water are called aqueous solutions, and compounds that are dissolved in water are denoted with the letters AQ in chemical equations. This is important to remember since many of the most common reactions that occur in solutions do involve aqueous solutions. We also need to introduce the term precipitate. Sometimes when a reaction happens in a solution, the product that forms is insoluble in the solution. It therefore forms as a solid and is said to precipitate out of the solution. This is language that chemists will often use, so it's important to have a grasp of it. Continuing on this theme, a precipitation reaction is one in which two soluble ionic compounds react inside a solution to produce an insoluble compound, which is then termed the precipitate. We can use two main factors to ascertain how much precipitate is likely to form. The first is reactant concentration. The more reactant is added, the more product is likely to be created. That should make logical sense. If it is assumed that a precipitate is the product of a chemical reactant, then it makes sense for higher reactant concentrations to produce more precipitate. The second factor is temperature. For aqueous solutions, there is usually a direct relationship between the temperature and the amount of precipitate. This is because, as we stated earlier, high temperatures tend to induce high solubilities for the soluble reactant compounds. Since the reactants are able to dissolve in the solution more easily at a high temperature, this favors the production of precipitate. Precipitation reactions are often double replacement reactions, and this will become obvious when we look at the chemical equations in our upcoming examples. One real-life example of a precipitation reaction is the formation of kidney stones. Kidney stones are typically comprised primarily of calcium oxalate. Calcium oxalate is not very soluble in water. It forms when calcium cations react with oxalic acid in a person's kidneys. The human body does have uses for both calcium and oxalic acid, and both of these compounds have a high solubility in water. When they react to form calcium oxalate, however, problems occur. Since calcium oxalate is not very soluble in water, which is the primary component of urine, it precipitates as a solid and begins to clump together into tiny crystals inside the kidney. Over time, these crystals can grow as more and more calcium oxalate is produced, until one day they form a discernible stone. Kidney stones must be excreted via urination, but because they are essentially crystallized spheres, they are very painful to pass. If a stone is large enough, it can even block the tubes leading out of the kidneys and thereby prevent urine from leaving, leading to an infection. We will conclude this video with two examples. Example 1. 5 grams of sodium chloride are dissolved in 100 milliliters of water. Concentrated silver nitrate solution is then added. Write the balanced chemical equation and determine the mass of silver chloride precipitate that forms. The procedure we're about to look at is the same general procedure used to solve solution stoichiometry problems. Our first job is to write out the balanced chemical equation. Don't forget the correct coefficients and the letters in parentheses denoting which substances are part of the solution and which one is a solid precipitate. This problem is a bit easier since it specifies that silver chloride, or AgCl, is the precipitate, so we know to write a lowercase s in the parentheses beside it. Determining the mass of precipitate begins by calculating the moles of sodium chloride that was added. We divide the mass, 5 grams, by the molar mass of sodium chloride to yield 0.0855 moles of NaCl. Because the chemical equation shows a 1-to-1 stoichiometric ratio between silver nitrate and silver chloride, we know that 0.0855 moles of silver chloride are produced. This gives us the molar value, but we want the mass value, so we multiply 0.0855 moles by the molar mass of silver chloride, which is 143.32 grams per mole, to obtain 12.25 grams of silver chloride, which is our final answer. Example 2 says, 0.35 grams of calcium carbonate is reacted with excess hydrochloric acid. The equation is provided as 1 mole of calcium carbonate reacts with 2 moles of acid to produce 1 mole each of calcium chloride, carbon dioxide, and water. We know that 0.13 grams of carbon dioxide are produced, and we wish to calculate the percent yield of this reaction. In order to calculate percent yield, we need to know both the theoretical yield and the actual yield. The actual yield is 0.13 grams of carbon dioxide, so we just need the theoretical yield. We start again with converting 0.35 grams of calcium carbonate to moles. 0.35 grams divided by the molar mass, 100.09 grams per mole, is equal to 0.0035 moles of calcium carbonate. Because there is a 1-to-1 stoichiometric ratio between calcium carbonate and carbon dioxide, we know that 0.0035 moles of carbon dioxide are produced. We multiply that by 44 grams per mole, which is the approximate molar mass of carbon dioxide, to get 0.154 grams of CO2. This is our theoretical yield. Percent yield is equal to the actual yield divided by the theoretical yield, all multiplied by 100. So dividing 0.13 by 0.154 and multiplying the result by 100 gives us a percent yield of about 84%. This question is an example of an acid-base reaction, which makes it a little different from the aqueous reactions that we have focused on thus far. However, we will discuss acid-base reactions in detail later, so this is a quick preview. The underlying solution stoichiometry is still identical. In the next video, we begin Unit 5 covering gases by talking about the states of matter. Thank you for watching.